Welcome to the 8th lecture of DCS 2. In this lecture, we will discuss about the design of heel slab. The last few lectures, we have seen how to design the stem, how to design the toe slab, and now we will see how to design the heel slab. So let us take the same problem which we have done for the stem as well as for the toe slab also. All other things being same problem we will extend it for the design of toe slab. I mean heel slab. Heel slab means this area, this portion. This is the heel slab. Yeah. So once again, the procedure is like the same. We will find out bending moment. We will check the thickness, whether thickness is sufficient to take the bending moment. Okay, and if it is found satisfactory, we will find out area of stiff. Then we will check the shear also. Then that procedure is complete. The design, analog is complete. So come back to the pressure diagram, the soil pressure diagram, which we have seen before. Last class we have seen this is 109.2, this is sigma max, and sigma minimum we found out like this, sigma W by B in 1 minus 6 E by B, which is coming 46.8, and our interest is this portion only. This is the heel slab. So this stress soil pressure also we need to find out, sigma 2, which we have already found out if I am right. This one using the similar triangles. Last class we discussed it comes around 54.6 kilonewton per meter square. This one, yeah, right. So this is our pressure diagram, soil pressure diagram at bottom, 54.6. This one, and this portion it is 46.8. Now in the heel portion, this is the heel portion, yeah. This in the heel portion, there are the pressure will develop because of three reasons. One is soil pressure acting upward direction. Because of the soil, because of soil we will have a pressure acting upward direction. Other one is you have a heel portion, we have sulfate. Sulfate will act down actually. So because of there is a pressure which will develop down. And in addition to that one, this is the soil phase. So there is a backfill is there for a height of 5.4 meter. For this 5.4 meter we have a backfill. So soil will also apply pressure this side. So backfill acting downward direction. This will also induce pressure. So these three pressures, only one is it upward direction, remaining two is downward direction. Okay, so this diagram soil pressure is only because of the soil which is acting upward. Yeah. So let us see. So this is the soil pressure which is acting upward. Sigma minimum 46.82, and at this location we found out sigma 2 which is 54.6. Now this is soil pressure, I mean the pressure diagram due to sulfate. You see, this is a sulfate will act. Okay, how do you calculate that? Because the thickness of this slab is 0.6 and the density of concrete, the unit weight of concrete is 25. So 0.6 into 1 meter, you are taking only 1 meter, yeah. 0.6 into 1 meter and 25 will give you 15 kilonewton per meter. This is 15 kilonewton meter. This is the indicates the sulfate pressure due to sulfate, the weight sulfate, yeah. It's acting downward actually. Another thing is backfill, which I have discussed here. This much backfill acting down here, this will also create pressure. So how do you calculate that one? The height is 5.4 meter. So 5.4 into 1 meter, this 1 meter length, into 17.8 is a unit weight. So totally you will get 96.2, which is also acting downward. This black color shows soil, this shows sulfate, and this is your actual pressure, soil pressure acting upward. So this is, let us say this is acting down, this is acting up, down, down. So what will be the effective? So this side 96.2 plus 15, both are acting downward, minus 54.6, which will give you 56.52. Whereas this side same 96.2 plus 15, both are acting downward, minus 46.2. So it will come for 64.4. So 64.4 you will get like this. Okay, 15 is acting downward, so 15 plus 8 plus 96, yeah, 96.2 acting downward, minus 46.8, this is acting upward. Okay, so that is the result is negative, so 64.4, and this side it is 15 plus 96.2 and minus 54.6, yeah. So net pressure diagram will be like this. It's the net pressure diagram, yeah. So now let's see here net pressure diagram. So now look at here, this is the retaining wall. See, this side it is acting downward, here it is upward actually. So here the tension will be at the top and here the tension will be at the bottom. So the main bar will come here, and the heel portion main bar will be coming at the top. It will be coming at the top. Okay, so let us find out the bending moment. So this is coming down, right? So the bending, we need to find out the bending moment at this location. This location we need to find out the bending moment. This point. Okay, here. So previous figure we have seen it is 56.52, and here it is overall it is 64.4. So if I divide into rectangle and triangle, this is also 56.52, this is same, this will be 7.88, yeah, 7.88, right? Yeah, 7.88. Okay, so the rectangular portion, the load will be acting at the CG. I am taking moment to this point, so this distance is x1, and for the triangular portion it will be acting at the CG, it is x2, it is 2h by 3, this is h by 2. Okay, your h is 1.8 meter. Okay, now x1, how do you calculate? X1 is total is 1.8, it is acting at the CG, so 1.8 by 2, 0.9. For x2, how do you calculate? This is 2h by 3, 2 into 1.8 by 3, because CG from the vertex it is 2h by 3, 1.2 meter. For calculating the bending moment, P1 into x1 plus P2 into x2, I am taking moment to this point, so this is x and y direction will come here, x1 and x2 will come here. So we will find out what is P1, the total force. The force is nothing but the area of the rectangle, and P2 is the force acting on the triangular portion. So area of the triangle will give you the force. So calculate it, 56.52 into 1.8 into 0.9, which is x1, plus area of triangle is half into b into h, 0.5 into 1.8 into 7.88 into 1.2, x2 is 2h by 3, 1.2. So you will get 99.52, which is m, and factored bending moment will be 1.5 into m, which is 149.3 kilonewton meter. So once you got bending moment here, then our aim is the thickness what you have provided here for the heel slab is sufficient to take this bending moment. That is a check, next check. So it's the same as that. Point out SP16. Using SP16 page number 10, table C, you find out mu is equal to 0.138 f secant BD square. This is the check we do for all, and using SP16 the same thing. SP16 mu, because we are using here Fi is 415 Newton per millimegapascal. So as per the SP16 page number 10 table C, it is 0.138 f secant BD square. Therefore from this we can find out D is equal to root of this one, all these things. So it comes around 208, meaning is that for taking care of for this bending moment 149.3, this 2 mm thickness is sufficient, but we have provided 522, total of 600 minus 70 minus 8, 522, so we are on the safer side. So what is next? So once you got bending moment, check also you found it is safe, then next is find out area of steel. It is the same procedure, yeah. So find mu by BD square. Mu is 149.3, this B is only 1000. So using that one you will get 0.54. Using SP60 table of singly reinforced beam, it is around 42 or 43, that page number it comes. The page number is coming around, it is like page number 49. This will be number 49. you will get PT is equal to 0.152. Our minimum is 0.12%, so we are higher than that, safer side. So once you got PT, you can find out AST like this, because PT is equal to AST by BD into 100. So from this you can find out AST. It comes around 814 square millimeter square. We use 12 mm dia bars. Using this small a into 1000 divided by s, you will get spacing is 130 mm. So it's not possible to provide 130 mm at site exactly. So you can go for 120 or 125 is fine. So let us provide 12 dia at 125 mm center to center, and the spacing should not be more than 3D or 300 mm. We are safer in this case, because D is ours is D is 522, okay, or 300 mm. 528 into 3 means 1500 mm or 300 mm, so which is less than 300 mm, so we are on the safer side. Next is find out the area of distribution steel, which is 0.12% of B into D. So it comes around 620, because substitute this one 0.12, you will get 626.4 for millimeter square. Use 10 mm dia bars. Okay, so you will get spacing is 125 mm center to center. Okay, so main bar is this much. So next step is you should check for the shear, this area. So as discussed before, the shear, the critical section is at a distance, the thickness of the slab from the face. So thickness is 0.6. So this is the critical section. This portion is the critical section. Okay, so we need to find out the stress at this location. So this is 1 point, total is 1.8. So 1.2, 1.6. So using similar triangles, sigma h1. You can find out sigma h1 is equal to 58.8. So using similar triangles, it's easy. So at this location, we need to find out the shear force. This is a stress diagram. 58.8 at this location, sigma h1. This is 64.4. Okay, so the area of this stress diagram will give you the shear force. Okay, how do you find out area? Convert into one rectangle and triangle. This is 58.8. So this will be 5.6 total. So shear stress is nothing but tau V is equal to VU by BD. Okay, tau V is VU into B. We are taking 1000, so 1000 into D. So how do you find out V? V is area of rectangle plus area of triangle. 58 into 1.2 plus half into 0.5 into 5.6 into 1.2. So totally you will get 73.8, and factored shear force is 1.5. Multiply with 1.5, you will get 110 kilonewton. So find out the shear stress. So 110 into 10 to the power 3 is converting into Newton, divided by B into D. B is 1000 into D is 522. So you will get 0.21 Newton per millimeter square. From the table 19 and IS 456, and you need to find out tau C. For finding out tau C, you should know PT. So PT we have already taken here 0.152. So 0.152 right now. Yeah, 0.152, not 0.156, 0.152. So using this, you will get tau C is equal to 0.3, which is greater than 0.21. So we are on the safer side. So this is the design. That's all. This is a summary of the reinforcement. Stem, because we have three parts: stem, toe, and heel. Stem main bar we got 16 dia at 150 centimeters. Main bar means at soil face. Okay. Distributor is 12 dia to 450. This can be, we can, if we are using 8 mm dia bars, then 8 dia, it comes around 8 dia at 200 or something like that. You can find it out actually. You can use it, because I think in the problems I have done it as using 8 dia. Okay. The only thing is that because your what is that? See this is your stem. So maximum bending moment will be here at the bottom. As you go up towards the free end, bending moment will be 0. So what you can do is, you don't need to provide this 16 dia at 150 centimeters throughout the height. So at h by 3 from the base slab, you can cut 50% of the main bar. Then another 50% at 2h by 3. So this curtailment, yeah. So which I have shown in the previous video. You can, I mean, previous PPT of stem design. Okay, now the top portion main bar is 12 dia at 180 center to center. Distributor is 12 dia at 180 center to center. Okay, and heel portion main bar is 12 dia at 125 and distributor is 10 dia at 125. So this is what I have shown here. See, stem 16 dia. This is 16. It's red color line, you know, that is your main bar. This is soil side. This is soil side. Yeah, this is soil side. Because here is our soil face. Okay, because it will try to bend this direction only. So this is the main bar, and you can just bend like this here, for instance LD, and this green color lines, you know, this is your distributor. See, 12 diet more 450, 12 diet 450, 12 diet 450, 12 diet, even vertical bar also distributor only, because distributors are not taking, it is provided not to take any bending moment. It is mainly to take care of temperature stress and shrinkage stresses, and also to keep the main bar in position. Okay, and now this top portion is this one, because 12 dia at 180 main bar means it is at bottom, because of soil pressure it will try to bend up, so bottom will be tension, top will be compression. So this is main bar will be at bottom. Okay, and distributor will be at top. This is all distributors, and our heel portion it will try to come down actually. So main tension at the top. So here is main bar, and we should provide a shear key. It is at 450, because we have seen if it is failing in the sliding, you know, just a default by default one 45 by 45 size shear key you can provide it here with the same this reinforcement. This will be sufficient. I think that's all.